The visible universe is only a tiny amount, about 4% of what the universe is actually made of. A very large fraction of the universe, in fact, about 26%, is made of an unknown type of matter called dark matter. Unlike stars and galaxies, dark matter does not emit any light or electromagnetic radiation of any kind, so that we can only detect it through its gravitational effects. An even more mysterious form of energy called dark energy accounts for about 70% of the mass energy content of the universe. In physics, the term light refers to electromagnetic radiation of any wavelength, whether it's visible or not. But too often when we say light, it is mistaken to mean optical light, which is roughly the radiation visible to our eyes. Visible light is a tiny portion of a huge smorgasbord of light called the electromagnetic spectrum. For convenience, we break this smorgasbord up into different courses, appetizer, salad, etc., and assign them names, such as gamma rays, X-rays, ultraviolet, optical, infrared, and radio. However, it is important to remember that they are all just light. There are no breaks and no hard boundaries in the electromagnetic spectrum, just a continuous range of energy. So let's do a thought experiment to appreciate light. Let's say in the course of a new year, I put you on a rocket ship and you come back exactly one Earth revolution later. I sent you off at 12 a.m. on a brand new New Year's Day. Well, if you're moving at typical rocket ship or satellite speeds, which are a few kilometers per second, your watch, if it's a good watch, will be about 1/100th of a second slower after a year due to the time dilation effects of special relativity and hardly noticeable. Big deal. But what if you start moving fast? What if you move at 10% of the speed of light, about 30,000 kilometers per second? Your watch will say that it's about 44 hours earlier than mine. While I'm ringing in the new year, you think it's 4 a.m. on December 30th. If you get up to 90% of the speed of light, I'm sipping champagne while you think it's early morning on June 9th of that year. At 99.99% of the speed of light, only 5 days will have passed for you while I have lived a whole year. And at 99.9999999% the speed of light, an entire year passes for me in just 23 minutes for you. So, as things move faster, time passes slower for them. Now, being made of matter and having mass, we can never move at the speed of light. But things that do travel at the speed of light never have any time pass for them. And so light never ages. Light never dies. And so what a great tool for an artist to try to understand. So with the science behind us, let's look at how artists can make the best use of an understanding of light to make really, really great drawings. And we're going to start with the absolute simplest example. So this is a simple light source hitting a very simple object, a sphere in this case. And light sources are not lasers. The beams of light are not absolutely straight beams. They kind of spray light. So when light hits the object in this particular case, the object is turning away from the light and the light cannot go around the corner. So the rotation of the form in this case cuts off the light at this point, and we're using astronomical terms here. So this line here is referred to as the terminator. And then this field of shadow here is referred to as a penumbra. And within the shadow field, there is what's referred to as a true shadow, where the light is truly blocked. And then there's a penumbra, where light is kind of spraying past the object that creates this kind of aura. And these terms will come up again in some of the following examples. This next example, example 2, gets a little bit more sophisticated. So as in the case before, we have a simple light source, we have a simple object. The object rotates away from the light and creates a light world and a shadow world. And to introduce some ideas that'll come up later, where the object is being struck directly perpendicular by the light, this area here is referred to as incident light. That's where the light source hits the object most forcefully. And then as the object rotates away, there's less and less and less light. But that fall off of light happens in a very particular way, and we'll discuss that really soon. The other phenomenon that we have to be aware of is that highlights, especially on a glossy object, highlights are brighter than incident light for reasons that'll be made clear in one of the other videos that I sent you. So this example introduces the idea of highlights, and that'll come back to us again. So here's where it really starts to get interesting and really useful to artists who want to draw well. This diagram is the basis for the difference between an okay drawing and an incredible drawing. And what this diagram shows is what Da Vinci knew about light through the course of his intense scientific study of light. So as in the examples before, you have a simple form being hit by a simple light source, but here's the catch. In this rotation of 90 degrees from here to there, let's say that this little band is 10% of rotation, this is another 10% of rotation, or 10 degrees of rotation. Because of how light works in the real world, there is only a 2% loss of light in this first 10 degrees, whereas in the last 10 degrees, there's a 17% loss of light. What that means is that as light hits this surface and the surface rotates away, the light falls off faster and faster as it gets towards the terminator. You can see here that if this is 50% of the way between here and there, the 50% loss of light doesn't happen until way down here. There's a very slow fall off of light at first, and then it gets faster and faster and faster and faster. What that means and how that's useful to us is that the fall off of light is not simple arithmetic like 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. The fall off of light is logarithmic. Slower at the beginning, then faster and faster until that last photon glances past the terminator point. And so to follow up on the previous example, here is the classic order of light, and here's how I want you to start thinking about light in your drawings. With this example, we add another factor. If you can see these little bouncing arrows here, that's referred to as diffuse reflection. In other words, when light strikes an object, the object doesn't absorb all of the light. Some of it is reflected back into space. In fact, some of the very, very early Flemish artists would actually paint the light aura around an object. They were that observant. But for us, let's look at the classic kind of stages of fall off of light. In fact, the fall off is infinitely smooth, but we can think of it in general in terms of some very simplified zones. So again, if the light is coming from here, this surface would be referred to as receiving incident light, but that's still not the lightest light. The lightest light is the highlight at zone 1. So let's go through the classic order of light. So The very brightest light is the highlight. The area around the highlight is referred to as light light. And then zone 3 is middle light. Zone 4 is dark light. Then there's light halftone, dark halftone, core shadow where almost no light is hitting from either direction. And then as you get past the shadow core, you're starting to get reflected light bouncing back onto the form. That's really important. So zone 7 is referred to as light shadow as opposed to dark shadow. And then there's cast shadow, but then within the cast shadow, there's this area where no light is hitting. That's called an occlusion crack. And then the cast shadow kind of spills out darker and then softer. And then also the cast shadow tends to be very sharp here and fall off very, very slowly. This is a really important diagram for the next set of exercises, which will be value spheres. So take a look at this really carefully. So here's the final diagram in this particular series to kind of wrap things up. You see here 4 different examples of value spheres. In this case, I added this illustration because in class I would have brought in a disco ball that I painted flat white to show you that as this object rotates, each one of these panels really has a different value. Your eye doesn't really want to see it, but that's the truth of light fall off. Each rotation has less and less light, and as you get toward the terminator, that fall off is faster and faster and faster, and I think you can see that illustrated here. So look at these examples again really carefully, because our next step brings all of this into play in value sphere exercises. And the value sphere exercises pick up with your gradient bars and your 10-step value scales. This is where all of this information really becomes useful.